All right. Hello, everyone. Welcome to the third episode of the LoRa Alliance Technical Webinar Series. My name is Alper Yegin. I'm the chair of the technical committee and vice chair of the board in the LoRa Alliance, and I work for Actility. I will be your host today. Before we begin, few housekeeping notes. Pushing F1 on your keyboard will refresh your screen in case you see there's a mismatch between the video and the audio. And there's also a toolbar at the bottom of your screen, and pressing the help box will direct you to how to solve technical issues you may be experiencing, just in case. And another helpful box, just below this video box is the Q&A box where you can submit your questions throughout the webcast, and we will be answering your questions live at the end of this webcast. Lastly, you will see the webcast resources list, a link to today's slides, along with some additional relevant materials. And let me introduce our speaker, Julien Catalano. Julien is the principal architect and head of standards working at Kerlink since 2013. He also acts as the chair of the technical committee, FUOTA, Firmware Update Over-the-Air Working Group at the LoRa Alliance since 2017. Based in France with subsidiaries in the US, Singapore, India, and Japan, Kerlink is a founding and board member of the LoRa Alliance. Julien has more than 15 years of experience in the Internet of Things industry, tackling embedded software development, system architecture, and strategic partnership in research, industrial companies, and startups. He's a strong believer in open standards, building them in several organizations, obviously including LoRa Alliance. And this sparked his recognition by the LoRa Alliance with the Working Group Leadership Award in 2019. It's been a pleasure working with Julien, and also a pleasure introducing him. So Julien, the floor is yours now.
Thank you, Alper. Thank you. Welcome, everyone. Welcome to the Firmware Update Over the Air webinar. So I'm Julien Catalano, and thank you for the introduction, Alper. So this is the agenda for our session today. So I'll have 4 points to discover a Firmware Update Over the Air building blocks with you today. So I will start with an introduction with a bit of history of the group and the specification we are building inside this LoRa Alliance working group. And then I will dive slowly into the specification themselves, first starting on explaining how Firmware Update Over the Air is working. And then we will go a bit deeper into the architecture of the specification. And finally, as the last point, we will deep dive into each one of the specification. So you will find all the specification we are talking about today in one of the screens below. You can download them; they are available for the public. So let's start first with a bit of history. So FUOTA, as we call it, is an acronym for Firmware Update Over the Air. It's also a working group of the technical committee, so the LoRa Alliance Technical Committee, which was chartered in 2017. The main goal of this group is to produce LoRa Alliance building block specifications for Firmware Update Over the Air. So as you might have seen and remember, we already released in September 2018 the first version of a bunch of specifications, namely 3 of them, and I will present them anyway today because we have released recently last month the new version 2 of those ones, plus a new edition of other specifications. But first thing first, let's have a remember of the history. So what you can see now on your screen is actually one of the first demonstration of what we have, what we built for the LoRa Alliance all-member demo in Philadelphia in 2017. Actually, this was a demonstrator built by myself actually, and what you can see on the screen is actually Alper's picture. Where we were taking photos of visitors and then broadcasting them using the specification we are building in the FUOTA Working Group over the air, over LoRaWAN, and to multiple devices at the same time. So you can see 3 devices on your screen there, where fragments were sent one by one, but to each device at the same time. So what I will explain in this webinar is how it works and what are the specifications we built to achieve that. What you can see as a little detail, which is important for the next part, is that you see missing parts of the picture. These are actually missing fragments, and this is one of the things we are tackling with our work. So the last part of this introduction is a bunch of highlights. What's important in the firmware update over the air specification? First of all, it's a security tool, meaning that it's one of the tools you have to correct, to patch your software in the field. So if you in any case you discover some security leak on your devices, you are able, using this tool to patch the software in the field without going there and patching them one by one. The second part is also one of the highlights of this work is that it's efficient on the physical layer. We are actually using physical layer broadcast, meaning that for every devices, a single data fragment will be sent by the network gateway to reach all the devices at the same time. So it's quite efficient on the radio layer part. And finally, and this is related to what I just described on the picture earlier, we use forward error correction. So this is actually linked with the physical layer broadcast in a sense that you can, so forward error correction allows you to reconstruct complete files even if some frames are lost. So the little white pixels you see there were lost fragments, and actually with the specification we built, forward error correction allows the devices to reconstruct those lost fragments without them communicating back to the network server and to the application server. But we will describe that in a moment. First, let's move on to the second part, which is how it works in a global view. So there are 3 steps. The first steps of a firmware update over the air session, what we design in the specification here, is that we need to configure each device in unicast. Then the second step is the firmware broadcast. So actually the file is broadcasted. And finally, we have an end of session where we achieve some other operation on devices. So I'll take them one by one, and we'll describe each a bit with a bit more detail. So first, there's the end device configuration. So it's important to understand that to configure end device, this is done one by one. So using what we call unicast configuration. So this brings the LoRaWAN security of the communication. So each device is contacted individually using the LoRaWAN security. And what we do in this step is that we actually use some clock synchronization to align every device clock to the same time, if necessary, of course. That's depending on the device capabilities. Then we set up 2 sessions. The multicast session first, where we say that at a given time with such radio parameters and such security settings, a multicast session will be sent by the gateway around the device. So the device can schedule the Class B, the LoRaWAN Class B or LoRaWAN Class C listening window at that time with those parameters and with that security context, so that it will be able to receive the data. And the fragmentation session, which is the second session we set up, is actually telling the devices what will be the size of the fragment it will receive, so the size of the firmware file, for instance, some integrity elements, so that the device is able to tell at the end that the file is complete and without error. And of course, what I talked about earlier, the error correction parameters, so which algorithm we use for error correction and stuff like that. So number of fragments of redundancy and so on. So this is the first part, which is, as I said, sent one by one to each device. This means that those scenarios are useful when there is a large file to send. If you only need to send one or two fragments to each end device, it might be more efficient to send them without setting up all those sessions. So the second part is about the file broadcast. So I said file broadcast because actually the specification is not specifically made for firmware. It's some building blocks for firmware. So it could be, but it could be any kind of files. So what happens is that the end devices, all the end devices which were configured in the first step, start listening to the multicast session all at the same time, due to the with the benefit of the time synchronization, of the clock synchronization we said earlier. Then each frame of the file, so the file is cut in many frames, in many fragments. Each fragment is sent once and only once by the LoRaWAN gateway. So over the air, if an observer is looking at the radio traffic, actually it will see a single frame going away from a gateway, and that frame is actually received by all the devices because they have all the same security context and all the same radio parameters listening to that broadcast. Finally, when the broadcast of the file is finished, some redundancy fragment can be configured to be sent. So those redundancy fragments are part of the forward error correction algorithm, and they are actually meant for each device to be able to reconstruct any missing packets. So this is something which is mathematically complex, but the devices actually receive, when they receive a redundancy fragment, they can use that one plus the fragments already received and do some calculation to reconstruct a lost fragment. So that's the second part of a classical FUOTA session. And the last part is actually the end of the session. So end of the session, the end device do two things. First, it stops listening as soon as the file is completely received. So even though the network keeps on sending redundancy fragments, for instance, if the device did not lose any of them or could reconstruct them earlier, then it stops listening as soon as possible. So this is to limit power consumption of the devices, and then the device goes back to normal operation. What the device can do, if instructed, is to report the fragmentation status. So it could happen, for instance, that some fragments were lost and unable to be reconstructed. There are some communication means which are brought by our specification, which allow to report such a status. It could also report a successful fragmentation reconstruction, for instance, to the server. On the other side, on the server side, the server can also instruct the device to get their status back. So it could check the fragmentation status, as I said. It could also request the current version of the firmware or the current version of the pending update of the firmware file on the device. And finally, we also build some instruction to ask the device to reboot. So all that is, again, used in unicast fashion. So the FUOTA server can instruct one by one each end device to do those checks on the firmware and on the reboot. So this is a wide view, a large view of how a firmware update over the year is designed in the LoRaWAN and the LoRa Alliance context. Now we will go a step further, looking at the FUOTA architecture. So this is the big picture. Don't get afraid. I will go one by one on each part so that you understand how it works. So let's begin by the first element. The first element of the building blocks is that we want to transfer a file. So what we designed is a file distribution service, which is actually not one of the specification, but a combination of many. So that's the main goal, to transfer the file, and we want to transfer a file to end devices actually. So these are LoRaWAN end devices. But we want more. We want to transfer a file to end devices via LoRaWAN, of course, and obviously we are the LoRa Alliance today. But we want to transfer a large file. So in order to transfer a large file, as you might know, LoRaWAN payload size are limited to a few hundreds of bytes. So if we want to send a large file, we need to fragment it. So the first building blocks we have is the fragmentation specification. So it's what I call frag here. So it's a mean to cut a given data block, a given file, a given blob of data into multiple pieces so that it could be sent over LoRaWAN to end devices. Actually, this is where in the fragmentation specification, this is where we describe forward error correction algorithm and integrity of the fragments and anything related. So we want to transfer a large file to end device via LoRaWAN, but we actually want to transfer to many end devices. So we want to transfer to a fleet of end devices. So in order to do so, instead of sending many fragments to each end device individually, what we design is a specification which enables the multicast station, so which enables to create and maintain a multicast station over end device, over multiple end devices. So as I said earlier, in the how it works, we first configure each end device individually so that they are capable to listen to that multicast station with the multicast parameters. So multicast parameters are the timing, when the session will start, the radio parameters, so in which type of multicast we will use. So in LoRaWAN, you have two choices, either class B multicast or class C multicast. So the difference is class C multicast is continuous listening. So the device opens a receive window at a given time and keeps on listening on that radio frequency and parameters up to the end of the window. For class B, it's slotted listening windows. So it's the same as the LoRaWAN class B in unicast, but then all the devices are in sync with the ping slot and the beacon of the LoRaWAN. So every device is synchronized, is time synchronized with the beacon, and then for each ping slot, it opens a receiving window and gets a fragment if we are sending fragments on each ping slot is configured to. So what is a bit specific about multicast is that each end device actually do not listen to its own device address, the divider in LoRaWAN, but actually a new device address, which we call a multicast address, is configured with that specification onto the device, so that they can find out over the radio if the message is for the multicast station or for their own usage in the unicast. So this is how we achieve sending that large file to many end devices at the same time. One more requirement we add was to be able to send a file to end devices over any version of LoRaWAN. So as you might know, LoRaWAN link layer has several versions already. So we are discussing LoRaWAN 1.0.4 these days, and 1.1 is also available. The firmware update over the year goal was to be agnostic to those versions. So in order to achieve that, all the elements of the file distribution and of the communication with the device are done via the application layer. So there is nothing specific in the LoRaWAN link layer. It's all handled on top of that. Next, what we want to do is to send that large file to a fleet of end device, but efficiently. So in order to be efficient, there's two efficiency. There's radio efficiency, which is achieved over multicast, but there's also power efficiency. And power efficiency is made with the help of the time synchronization specification. So with that spec, we allow any end device to be synchronized, to have its clock synchronized closely to the network clock. So it's 1 second accuracy or a few seconds accuracy, so that it can start the multicast session at the right time and do not listen for days or for hours without any packet coming in. So with time synchronization, we can open the listening window at the right time and close it as soon as we receive the full file. So this is what I call the efficiency on the power. To add more efficiency on that, as you saw, we have many specifications, many messages to send to the device in unicast at the beginning of the session. We built what we call the multi-packet access specification. And this one is used to bundle several messages from a different application layer into a single downlink. So this allows, instead of having one downlink to configure fragmentation, one downlink to configure multicast, one other downlink to do the time synchronization, those three could be concatenated together and sent in a single master downlink, I would say, or meta downlink to the device, and the end device could react and reply to those downlinks in a single uplink again. So this achieved the efficiency. And finally, what we want to achieve is actually sending a firmware file, a large firmware file to the fleet of end device. So the last specification we will be talking about today is the firmware management specification, which is actually quite light because there are many things which are manufacturer specific. I'll come to that. So this specification is the only one actually related to firmware, where you could ask for firmware version or ask for update version, ask the device to reboot and stuff like that. So this is it. This is the full architecture of the LoRa Alliance firmware update over the air specifications. One last thing you might be wondering is those numbers, 201, 202, those 203 and 225 numbers are actually the recommended or specified frame port of each package. So as you saw earlier, each package could be addressed individually, and each one have a dedicated F port, so that the application layer on the device can find out and know which package is actually targeted when the communication is coming. So lastly, on that part, I would like to emphasize what was not addressed, not because we didn't want to, but because actually we found out that it was out of the scope of those specifications. There are a bunch of things which are manufacturer specific. So when you update the firmware of your end device, actually the file format, the way the device will take it and install it, is rather manufacturer specific, specific to the OS, specific to the runtime you have on your device, specific maybe to the security of that file. The security check might also be specific to the implementation. So this is not addressed, and you will not find that on our specification, which is limited to sending the file and addressing the file, the fragments distribution over LoRaWAN. Another part which is not addressed on this specification, because it's actually also very dependent on how it's implemented on the device, is the efficiency techniques of firmware. So, for instance, having delta updates, so sending only firmware patch, how to install a firmware patch. This is something addressed by other techniques. And finally, You might wonder how to do network planning, how to select which gateway will be broadcasting the firmware, how to choose the timing. So this is left to the network operation vendors, and this is not something we address. So this is the big picture of the firmware update over the air specification. Now, on the last part of this webinar, I would like to present them each. Then I would like to present each of them. So let's go to the specification deep dive. So you can see on your screen the full name of the specification. There are five of them. Sorry. So they are numbered as any specification released by the LoRa Alliance. And today we will be addressing the technical specification number 3, which is the application layer clock synchronization. So this is one we have released recently in version 2. Technical specification 4 is the fragmented data block transport. So this has also been released in version 2 earlier in April. Technical specification 5 is the remote multicast setup, also in version 2. So those 3 specifications have been released in 2018 in version 1, and today they come in version 2. So for each one, I will highlight what's new, what changed on those, and how they work also. Technical specification number 6, the firmware management protocol has been released, and it's a new specification released in April this year, and technical specification 7 as well for the multi-package access. So these ones are new and were not present earlier. Okay, so let's start with the first one, the application layer clock synchronization. So this is a simple one, so I will take this opportunity to explain a bit how they work, all of them a bit in details. So every single specification we will be talking about today are actually application layer specification, meaning that they rely on the LoRaWAN link layer, but they do not need anything from the link layer except that it's there. So the application layer clock synchronization is actually there. The purpose is to synchronize end device clock. So each end device might have will need a clock synchronization to start the multicast station at the right time. So that's one of the purpose, having each end device synchronously start the multicast station. But it could be also used for other means. So that's also one of the thing of building each part in a standalone specification is that, for instance, time synchronization could be used to perform synchronous measurement of scheduled action, like switch on a light or open a gate at a given time. So it could be used for all the other purposes, even though they were designed for the firmware update over the air main goal. One point of attention here is that it's important to understand that this is good to synchronize action on the device, but it should be taken care of, never synchronize any transmission or any reboot. So why is that? That's because when you synchronize transmission, if you have thousands of devices which are in sync for transmission, the network will fall out. So this is very important to use that specification not to synchronize transmission nor reboot. Reboot is important as well because usually end device firmware when they reboot, they do a join request. So even though we have that backup mechanism for a join request, it's important not to synchronize the reboot. So having a random delay before any transmission or before any reboot. So that application layer clock synchronization is actually useful when there is no other time source on the device. So some devices, especially a recent one, can implement other time synchronization source. So the main one in LoRaWAN is actually the device time rec, which is something which is used in Class B, for instance. But your device could also use a real-time clock, so RTC, or even have a GPS receiver, so it could synchronize its clock source. So as any of the specification we have in firmware update, if it's not needed, it's not mandatory. So for each one, I will also present that kind of table. So that table is actually the command list you will find in the first pages of each specification. And it's always structured like that. So you have the command ID on the left-hand side, starting at 0. Here we have four commands, commands and response name, and the way they are transmitted, and a short description for each. So for this application layer clock synchronization, we have the usual and every spec as this one, the package version rec, which allows the server to request the device to know which version of the package the device is running. As we are releasing version 2 of this one, this is important for the server to know that it's a version 2 or a version 1 package implementation, because there is a few difference. So for each specification, for each package, we have this package version rec and ANS, which allows to discover or to request the device implementation version of each package. Then we have the main meat of that specification is command ID 1. It's the app time rec. So actually, it's used by the device to request a clock correction. So the device could be configured to send that command regularly, and the server, which is keeping track of time, could answer with some time correction. The main benefit of this implementation, this specification, is that if there is no correction to make, the answer is optional, meaning that the device could send that app time rec from time to time, but if there is no need for correction, there is no need for answer, and then radio-wise, it's quite efficient. So there are also some configuration options with the device app time periodicity rec. So that's a command coming from the server. It's command ID number 2, and it's used for two purposes: either to set the periodicity at which the end device shall transmit the app time rec, so you can change that dynamically, or to request an immediate transmission of the end device time. So for instance, if the server finds out that the device is out of sync, it's willing to, when it has an opportunity to send a downlink to the device, it's willing to ask it to send app time rec immediately. So there's the pending answer, the device app time periodicity ANS, and the last one is the force device resync command, which is sent by the application layer to trigger a clock resynchronization. So as I said, this is this is version 2 of the spec. So what's new is that actually we found out that version 1 was having an issue with the app time rec and the ADR in LoRaWAN link layer and ADR and mid-trans. It was actually transgressing some rules of the LoRaWAN link layer. So we fixed that, and now the clock synchronization specification can be aligned with the link layer. And the second new thing, it's adding some iterative clock adjustment. So this is a novelty. When the clock is really out of sync, the syncing could take multiple cycles, and this is added. So this is it for the first one, the clock synchronization. Let's go to the next one. The next one is the fragmented data block transport. It's technical specification number 4, and the main goal. So again, it's an application layer, and the main goal is to send a fragmented data block to a group of end device. So actually, this one could be linked to the multicast, even though it's not mandatory. It has some knowledge about multicast, so it could be used in unicast or multicast. It could, so it's built to set up and maintain a session, a multicast fragmentation session, sorry, with some integrity and authenticity check of the fragments. So we are sending in the setup of the session, we are sending a MIC, a message integrity check, which is allowing the end device after the reconstruction of the fragment to check the integrity of the data block. And finally, and we talked about that a lot already, this is the specification which is enabling forward error correction. So this is the command list. It's actually a bit longer than the previous one, obviously. So we still have the package version rec and ans as command ID 0, and that's the same purpose as earlier. So I will not explain that again. Then we have 3 commands to set up, delete, and having the status of a fragmentation session. So actually, so command ID number 2, it's not the next one, but number 2, it's actually setting up the session on the end device. So sending the site of the fragment, which will be broadcasted later, sending the number of redundancy fragment, the integrity, etc. The status is actually command and answer. So command ID number 1 is there to ask an end device either in unicast or multicast, and this is something which is specific to this one, to send the status of the fragmentation session. So in the details, if you look in the details in the specification, you'll see that if that requested in multicast, so if the server is sending a multicast message with the fragmentation session status rec, every end device will not answer at the same time. As I said, they will spread out their answer over time, and there is a parameter to configure that spreading. The command ID number 3, so fragmentation delete, request and answer is actually there to delete a session, so to clean up the session memory, etc. And finally, the main part here is the fragmentation data block receive rec. So there, it's used by the end device. So command ID number 4, it's used by the end device to signal the fragmentation server that the data block has been completely received. So this is what we described in the end of session of the FUOTA session. But the main part is command ID number 5, which is actually not a standard command ID, because it's actually the actual fragment. So that message ID, the command ID 5, is followed by a fragmentation number, and then you have the raw fragment, so the slice, what we cut off the data block, which is sent to the device. So command ID number 5 is actually the one that you'll see the most over the air. So what's new in the fragmented data block transport specification version 2? Actually, we added in version 2 this cryptographic integrity check, which was not present in the first version. So to have an integrity of the data block, at least some capacity for the end device to check that the data block is without error, and that's actually the one intending to be sent by the fragmentation layer. Note that this MIC, this message integrity code, is different for each end device because it's configured in unicast to each end device. So it's the security it chooses is the unicast link security, not the multicast one. So we fixed some security and we correct some stuff on the fragmentation session. So it's there where we had some key exchange, etc. And we also clarified a lot of things on the spec. Okay, let's move on to the multicast session. So that's the remote multicast setup specification, the technical specification number 5. It's again an application layer. which is there to program a temporary multicast session into a group of end device. So that's the one where we create and manage multicast group remotely with the security context. So what we configured is the timing. So that's the second point, actually, the Class B or Class C timing for the multicast session, and the keys, so the multicast key for the LoRaWAN protocol, the counters, and all the security context we get for multicast. So again, and I think I will go a bit faster on this one. We have the command ID list with the package version as usual. We have, again, setup, status, delete commands, which are there to set up the multicast group, request the status if it's present or not, and delete it if needed. And so that's command ID number 1, 2, 3. Then we have command ID 4 and 5, which are multicast Class C session rec and multicast Class B session rec. These are separated because actually they do not use the same parameters to configure the device. It's close, but it's not the same. And that's it for this specification. So again, this is a new one. We had version 1 in 2018. What's new in this one? Actually, what has been clarified is the usage in Class B and Class C, which was brought up by the interop test we made inside the LoRa Alliance working group, the FUOTA working group. So that's clarification, and we also complement the specification with more details for interoperability about usage of counters, keys, and device address, multicast address generation. So it's closer to version 1 than the others, but there are some clarity and new information for interoperability. Okay, two specification left. The technical specification number 6 is the firmware management protocol. So it's again an application layer. It's to manage the firmware on an end device. So as I said, there is many things which are left to the manufacturer's specific side, but still we have the minimal commands to query versions on the devices to reboot them at a given time. So we have twofold. Either we can reboot at an absolute time, so at a given date and hour, or at a relative time, so meaning in that many seconds you will reboot. We can also use that specification to query the firmware update image presence and version, so to know if there is some update ready to be installed and which version. And we can also delete a firmware image with that specification. So it's minimal, but it's useful, and actually it's useful for firmware update, but it could be also useful if you have any use case where you need to reboot your device or need to query the firmware or the hardware version of your device for device management purposes. This specification could be used as well. And finally, the command ID, yeah, so you get the package version rec again as command ID 0. Then command ID 1 is the device version rec. So there it's meant to ask an device for its hardware and its current running software version. You get the same one as command ID number 4, which is actually the firmware update presence and the version. So is the update there and what's the new version? Then you have command ID number 2 and 3, which are used for programming a reboot. So either immediately or at a given time or after a certain period of time for the command ID number 3. And finally, command ID number 5 is used for deleting an update. So if you have an image pending on your device and actually you don't want to use that one, or you want to get rid of it, then this command is useful. So last part is and this is the last specification. This is the technical specification number 7, the multicast packet access. So this specification actually has two purposes. So it's a meta specification because it's actually there to be used with others. It has no use by itself. It will be only useful if you have other packages to communicate with your device. So the first part is to query device packages on end device. So actually it's very related to the package version rec on each end device, but on a single message. And it's also defining a protocol to access multiple packages, as I said, with a single domain. So you could query packages with their version F port and also access those packages and response. And one thing which is tackled by this specification is response fragmentation, because there are some regions in LoRaWAN where the uplink size of the payload is actually much shorter than the downlink one. So if the query is too large, then the response might be fragmented. So there are some mechanism here to help the fragmentation of the response. It's quite light on the commands. So you get itself the package version rec and ANS for this package, but also the device package rec, the command ID number 1, which is actually used to request all the packages installed on the device. And then command ID number 2 number 2 is used for the fragmentation answer, so the fragmented answer. If some fragment is lost, I can ask again for the device to send it again. Finally, this multi-package access specification is bundling commands, so multiple commands in single downlink, and this is how it works. Actually, it specifies that first the packet is built with the package ID, then the command ID of the package of the given package, and then the command payload, and so on and so on. So actually, that's how we bundled many commands and commands from many packages into a single payload. And this is it for the LoRaWAN firmware update over their building blocks. So thank you for listening. I keep the picture for the question, and back to you, Alper.
Thank you, Julien. Thank you very much for this very comprehensive introduction to the LoRaWAN FUOTA feature. Before we proceed to the Q&A, I would like to make two more announcements. The first one is the upcoming LoRaWAN World Expo event to take place in Paris in July 6 and 7. This is the largest LoRaWAN event where we will be having numerous presentations, seminars, panels, and demonstrations throughout the whole ecosystem. And there's also an exhibition area, and that's a very good opportunity to meet the rest of the ecosystem and also meet Julien and the FUOTA Working Group in case you still have questions after today's session. And secondly, the next webinar in our LoRa Alliance technical webinar series is the Augmenting LoRaWAN Devices with the Internet Protocol Support, which is about transporting IPv6 over LoRaWAN. So that webinar will take place on June 14th, and you will have the link to register for this event as well. And now that brings us to our Q&A session. All right, so, well, we already have numerous really good questions from the audience, so let's go over them one by one. So the first question is from Marco. Marco is asking, can end devices still send their data during a multicast session?
All right, that's actually a good question, and the answer is yes. The only caveat is that when you are receiving a multicast downstream, actually, as LoRaWAN is half duplex, you will not be able to receive fragments. So either you lose it or you go in between two. but it's possible, but you might lose any fragments.
Right. Then the next question from Uzair is, how much fragments can be missed by an end device and still the file be reconstructed successfully?
Oh, okay, so that's also, we don't have a clear answer to that. It's depending on the configuration of your broadcast. So the fragmentation session could be configured to send, for instance, many reconstruction fragments, so you could be able to reconstruct more. And the second element is the device capacity, the computation capacity. As I said, it's quite complex mathematically, so some device might be more powerful than other to be able to reconstruct more loose fragments.
So it's a tuning parameter depending on the network quality as well, right? A lot of parameters have to play together to optimize the performance. All right, and another one from Marco again. How does the FUOTA server handle end device on different data rates in relation to appropriate fragment size?
So actually, during the configuration of the multicast session, the data rate is configured on each end device, as I said, individually. So if you want to configure devices with multiple data rate, then you have to either have different sessions, so timing session on the multicast, or you have to be below under different stream of LoRaWAN streams, so different gateways or a different session from the same gateway. That's otherwise, if you build a single multicast session with the same parameters, you need to configure all your devices with the same parameters.
Mm-hmm. Mm-hmm. Yeah, because we're using the physical broadcast, we cannot accommodate different data rates, right? So all end devices have to receive using the same data rate. All right, the next one from Luca. Has the time sync to be GPS time, or can we also use NTP coming from a web server?
So I guess the question was asked a bit before I presented the time synchronization package. So if your device can be in sync using NTP, that's fine. And actually, you don't need the clock synchronization package from our spec. But be sure to be on the GPS epoch time because this is the time reference we use in LoRaWAN.
All right, and the next question is there an open source implementation of FUOTA? Let me jump onto that one. The LoRa Mac implementation from Semtech does support FUOTA, and yes, we do have one. All right, the next one from Alessandro. What should be the maximum size of the firmware update?
Okay, so that's an interesting question as well. Size is also a matter of end device capabilities, capacity, and also network capacity. So usually what we've been designing the specification for is a few hundred of kilobytes for the fragmentation, because if you go higher than that, so a few megabytes, it will get very difficult to get the reconstruction parameters working well. So we targeted around a few hundred of kilobytes, so 200, 300 kilobytes of firmware update of file transfer for the fragmentation. If you don't need fragmentation, or if you don't need reconstruction, then you can do as much as your network can be.
Yeah, it's also in the interest of the network to minimize the amount of data being pushed, right? In order to have more capacity. And also in the interest of the end device, not to minimize the file size in order to preserve battery. So we always encourage the implementation of networks to optimize the firmware size as much as possible for all these different factors.
Yeah, and in addition to that, there are, as I said, multiple techniques for compressing the firmware update or having delta firmware update, for instance. So this is some techniques you can use to reduce the over-the-air data transfer.
All right, the next one from Alessandro. Every device class A, B, or C can do FUOTA?
Yes, they can. Actually, the specification we built for the multicast session setup is that a device is supposed to be in class A and the multicast station is started either class B or C, and it's a temporary multicast station. So you need to support that, such a feature, but if you do, then any device can do FUOTA, indeed.
Mm-hmm. Right, so during the FUOTA session, device is both in class A, as usual by default at all times, and also either in class B or class C to accommodate the multicast downlink, right?
Yeah, right.
Okay. And the next one is Claudio asking, in a dense setup where you have devices under the overlap area of more than 2 gateways, what is the mechanism to avoid, sorry, the screen's shifting. What is the mechanism to avoid the device gets confused by the FUOTA activities coming from different gateways? So multiple gateways transmitting the same frames. How does the system deal with this situation?
Okay, so this is what I've been calling the network planning. Actually, it's some intelligence you need to have in your on the network side to avoid such a conflict. And if you do receive some conflict, it might indeed confuse the device. The network planning is quite important there if you have a very large fleet of devices and very large area to update.
All right, the next one is from David. It seems like there's little support for Class B. Few vendors of end device of gateways support it. Also, there are few articles on development and operational experiences. What actions are being done by the LoRa Alliance and others to promote adoption of Class B? So yes, it is true that Class B is a more advanced, let me jump in here. So it is true that Class B is a more advanced mode of operation compared to Class A and even Class C. And that's why you see a lot of devices and networks supporting Class A, but less so on the Class B. Nevertheless, there's been new deployments coming up with Class B. Most notably, KPN in Netherlands have deployed nationwide Class B, and Class B is also pretty critical for not only for the firmware update over the air, but also for remote control of end devices like gas meters, water meters, to shut them off in case the bills are not paid, or in case of an emergency, shutting off a group of end device all at once. So expect to see more deployments of Class B moving forward. All right, we still have some more time. The next one is from Marco. Can an end device request for a missed fragment?
So the short answer is no. It's designed for that. So actually, the forward error correction we built do not require the device to ask for a missed fragment. Short answer is
David is, sorry. And David is asking, is there a spec for fragmentation of messages sent from devices to the LoRaWAN applications in the reverse direction?
Okay, so that one is interesting actually because we have many answers. So the first one is the multi-package access protocol that I described in the last part, where you have it's very specific, but we have a specific fragmentation for answers of this multi-package access due to the constrained uplink size. But actually, there's another answer which might be a bit more interesting to you. Sorry. But it's on another standardization organization. The IETF has actually standardized what they call SHIC, which is a compression, a header compression and a fragmentation protocol, which is working over LoRaWAN. So such protocol could be used for fragmenting uplinks as well.
Right. So, I mean, even though there are ways to fragment uplink frames, we certainly recommend the ecosystem to be as efficient as possible, packing as much information into smaller payloads, right? Just because there's fragmentation, the application developers freely using it to send a lot of data is not advisable, because doing so would consume more battery and would eat up more network capacity. So please do use these tools wisely. Okay, the next one from David. Are there example implementations of applications that support the new protocols, specifically TS3, clock synchronization?
So I don't have any example in mind. Maybe you do, Alper. I think
no, I don't either. Yeah,
so
within our own
social networks, but I'm not sure they are valuable.
Yeah, I mean, within the specifications that we've been developing in the LoRa Alliance, only FUOTA is using that, and the rest is left to the ecosystem. You know, instead of building their own application layer proprietary signaling for this, here's what we provide to them. All right, the next one is from Troy. If an end device supports FUOTA, will that require additional LoRaWAN certification testing?
So that's also a good question. Actually, certification is not yet available for FUOTA stacks, but it's ongoing work inside the LoRa Alliance. So get prepared to have some new certification, yeah, for the FUOTA specifications.
Okay, so let's extend the time a little bit more because there are really interesting questions here. The next one is okay, from Alessandro. Where should be the FUOTA service, in the network server or the application server?
So that's what I've been describing during the application, each specification application description. So they are in the architecture at the application layer, and the main thing about that is to be able to be using LoRaWAN link layer at any version. But they need quite a close interaction between the application server and the link layer server, so the network server. For setting up a multicast station, for instance, the network server needs to provide some information to the app. So it's at the app layer by definition in the architecture.
All right, and Alexander is asking, will TR number 2, the FUOTA process summary technical recommendation, will it be updated also?
So actually, that technical recommendation already describes the FUOTA flow in a very high view. We do not describe in that flow the firmware management or the multi-package access, but there are details. We might upgrade it, but it's not yet planned. The principles in that TR are still relevant.
Yes. Okay. And this one is question number 26. During a fragmentation session, how do I choose on the server side the period between each fragment transmission?
Oh, that's an interesting question. How do you choose the period between each fragment? So if you are using class C multicast, you could send them back to back. So there is no need to have time between fragments. And actually, the more time you add between fragments, the more power you will use on the end device side, because the end device will be in a continuous receiving window. If you are using class B, actually it's a slotted transmission in class B, so you could choose from 1 second periodicity ping slot to 128 seconds, and that's up to your network planning as well, I would say. So there is no specifics. Oh yeah, there is one specific thing to take care of is the regulation duty cycle. So for instance, in Europe, if you are using the 10% duty cycle band for a downlink, then you need to take good care of not going above that limit. So maybe class B 1 second is not appropriate there.
Right. Okay, so let's take one last question as we are over time. This one is from Junaid. Does the fragmentation sequence matter? How can one upload firmware? Is it on the network server side? Let's start with the first one. Does the fragmentation sequence matter?
So it does not actually. Each fragment is numbered. We have a numbering which is up to 14 bits, sorry, so you can have that many fragments. And actually, if they are received out of order by the end device, it's not an issue. The end device is supposed to place them on the correct order in its memory. And moreover, when you receive forward or correction fragments, so coded fragments as we call them, then they are there, and they are not specific to a given fragment, so they can reconstruct not any, but they can be used to reconstruct any loose fragment on your data block.
All right, so we are already over time, and that's been pretty interesting set of questions. And so let's stop here and let's adjourn our webinar. Thank you very much once again for participating in this webinar, especially with this really interesting set of questions. And thank you, Julien, again for this super informative webinar. And please do stay tuned for our future webinars from the LoRa Alliance with the within the technical webinar series. And until later, stay safe, and let's meet again in a future event.
Thank you, Oliver, and thank you, everyone. Bye.
Bye.